Okay, so for 201, today our lesson ended here on the think pair share. Do you think that the concentration of an acid would affect the strength of an acid? And can a weak acid ever have the same pH as a strong acid? Okay, think about it. You can try writing down some notes as to whether you think it is correct or wrong and your reason. Okay, let's move on. Okay, so does it really affect the strength of an acid? No. A weak acid always dissociates partially, and a strong acid will always dissociate fully, regardless of its concentration. Okay, so let me just write something down. Okay, so when I increase concentration of acid, what I do is, how it keep disappearing? It will lead to an increase in concentration of your hydrogen ions. Okay, this is definitely true. But is your definition for strength a high concentration of hydrogen ions? No, right? The definition of strength is dependent on the degree of dissociation. Okay, something wrong. Degree of dissociation. Okay, so a weak acid always dissociate partially, not 100%. Whereas a strong acid always dissociate 100%. Okay, so I'll explain more later. You just copy this down first. I will give you an analogy later. Okay, now can a weak acid have the same pH as a strong acid? You may think that that's not possible. A weak acid should always have a higher pH compared to a strong acid, right? Okay, not true. When I make my weak acid very concentrated, and when I make my strong acid very diluted, it can still give them the same pH. Note, pH is a measure of the concentration of H plus. Okay, so it is only dependent on the concentration of H plus. Even though weak acids by itself they do not dissociate 100%, when I increase the number of acid molecules, ultimately I can still have the same number of hydrogen ions as a diluted strong acid. Okay, how can I explain this? Okay, here's an analogy. Let's say that Miss Cool, me, am in a soccer game with Cristiano Ronaldo. Okay, if you don't know him, he's a famous soccer player. Okay, so I am a weak player in soccer. My strength is weak. Okay, I can only score 1 goal per game. Okay, let's take it that he is strong in this basketball game, and of course he's able to score 10 goals per game. So when I am in a match with him, who do you think will win? Of course, Cristiano will win, right? Ding, ding, ding. Okay, and I will lose. Why is that so? Because he is something like a stronger acid. Okay, you can think of it as strong acid and a weak acid. Okay, so the number of goals scored is equivalent to the number of H plus ion that's produced at the end. Okay, let's take it like this. So a weak acid always give less hydrogen ions compared to a strong acid if they are at the same concentration. Okay, so the concentration here refers to the number of people per team. So if it's 1v1, of course he will win. Okay, so what about if I have a team of 10 people? Okay, we all have the same strength. It is clones of me. Okay, versus one of him. Okay, even though individually I'm weak, I can still only score 1 goal per game, but as a summative effort, now I can score 10 goals. 10 goals. Whereas he also scored 10 goals, and in this game we become tie. Okay, it's in a tie. So you can think of it as the concentration of H plus on both sides is the same. Okay, what I do here is I increase the number of people, which is equivalent to increasing the number of acid molecules. Okay, so when I increase the concentration of a weak acid and dilute a strong acid, you can see that it is possible for us to achieve the same concentration of hydrogen ions, and hence giving us the same pH. Okay, so take note, the strength of an acid is never determined by the concentration of the solution. Strength is inherent in the nature of the acid, just like how my strength in soccer is inherent in me. Even if I clone myself many times, I am still weak individually. Okay, he is still strong individually, even if there's only one of him and there's a lot of me. Okay, our nature does not change. What is changed is the number of hydrogen ions. Okay, so that's it for this topic. You can write down your own analogy in the space that's given in your notes. Okay, so now we move on to salts. Okay, here's a joke. Okay, NaCl is a salt. Okay, so what is an example of a salt that you know? Most likely you'll tell me table salt, which is like NaCl. Do you know any reactions that produce a salt? Okay, it will be all your acid reactions and your alkali reactions. So, what then is the definition of a salt? Okay, the definition is a substance formed when the hydrogen of an acid is partially or wholly replaced by a metal or ammonium ion. Okay, can you copy this down first? Copy this down first. I know it doesn't make sense. I'll explain the meaning here. Okay, so what happens here is, for instance, this is the example that's in your blanks. H2SO4. Let's say I wholly replace, there's 2 hydrogen ions here, right? So if both hydrogen ions were replaced by a metal, let's say your calcium, this is a salt. Okay, when I replace the hydrogen with a metal cation, it is a salt. Now, what does it mean by partially replacing the hydrogen ions? Okay, again, there's 2 hydrogen ions here, right? So, if I don't replace both hydrogen, I only replace one but keep the other. Okay, this is an example of partially replaced. This is also a salt, but take note, this is an acidic salt. Okay, why is this acidic? Okay, now NaHSO4, I can break it down into your cation and anion as usual, right? So Na is Na plus. What is SO4? HSO4. It should have a charge of 1 minus, because Na is only Na plus. There's 1 Na. It means that this whole molecule should be just 1 negative charge. Correct? Okay, now HSO4 can be further broken down into H plus and SO4 2 minus. Okay, so the reason why it is considered as an acidic salt is because that you have your hydrogen ions being further produced, even if it's a salt. Okay, so since this salt is able to produce H plus ions in water, it is considered as an acidic salt. Okay, note that by default, usually when we talk about salts, we consider it as wholly replaced. Okay, when you are writing your equations, you always assume that the salt form is a wholly replaced salt. Okay, partially replaced. All you need to know about partially replaced salt is this example. Okay, when you see that it is only partially replaced, you know that it is an acidic salt. That is all you need to know. Okay, so do not be too confused about the partially replaced by a metal. Okay, now we say it's either a metal or an ammonium ion, right? So this is the last example. Okay, in your notes I wrote HNO3. Can you change it to HCl? Sorry, I wrote the wrong thing. Okay, HCl, and the H is replaced by an ammonium ion. Okay, is it possible for it to be your HNO3 also? So HNO3, when it's replaced by ammonium, you will get NH4 and O3. Do you think this exists? Yes, it does. Okay, so this is also legit. Can? Okay, this is just an example of how you can replace the hydrogen with your metal or ammonium ions. Okay, so what is the salt? Can you try and fill in the table? Oh, try and fill in the table that you have where the acids, the hydrogens, are being replaced by the metal that's specified in your table. Okay, try it now. Pause the video and try it now. Okay, ready? Okay, here's some answers. Okay, you notice that I left out your phosphate. What's this called? Phosphoric acid. Okay, H3PO4. I will form Na3PO4, Ca3PO4, 2, and your Al PO4. Looks weird, but those are the correct answer. Okay? Now, let's continue. So, what do we need to know about salts? You must know the solubility of the salts as well as the bases. So, you need to know about your solubility of your nitrates, chloride, sulfates, as well as your carbonates, oxides, and hydroxides. Okay, so how do you memorize the solubility of salts? Okay, can you just put a star there? Okay, you must memorize the solubility of salts and bases. Why is it very important? Because without this, you are not able to write your state symbols. Okay, you want to know how to write state symbols, right? For your equations. If so, you must memorize this solubility. If not, you will not be able to write the correct state symbols. Okay? Now, the one that's always soluble will be your group 1 metal salts, your nitrate salts, as well as your ammonium salts. There are no exceptions. So this is the rule that I always follow first. There are no exceptions. Later I'll show you some examples. Okay? What are salts that's mostly soluble? Your group 7 salts. What is group 7? Okay, group 7 is your chlorides. Okay, as well as your fluoride and iodides. Okay, but now you just need to memorize your chlorides lah. Okay, chloride sulfate. So the exceptions are your A, B, C, and PB. Okay, this is how I remember. AgCl, remember what's AgCl? It is silver chloride, then barium sulfate, calcium sulfate, and lead chloride and sulfate. Okay, mostly insoluble. Okay, carbonates, metal oxides, and hydroxides are generally insoluble, except for the cases that we've mentioned here that's always soluble. Okay, so I can do this in a flowchart. Okay, First thing that I'll ask myself when I look at a salt is it from group 1 or ammonium? Okay, if yes, it is soluble. If it's not from group 1 or ammonium, I ask myself, is the anion a nitrate? If yes, it's also soluble. Okay, if no, I ask myself, is it a carbonate, oxide, or hydroxide? If yes, it should be generally insoluble. An exception is your calcium hydroxide is slightly soluble. Okay. Now, next, if it's not these three anions, is it ABC, PP? PP mean lead. Okay. So these are the examples you should know that is insoluble. So if it's ABCPP, it's definitely insoluble. If it's not, it should be a soluble salt. Okay, because if it's not, it's a chloride or sulfate, it should be generally insoluble. Okay, so it's very important for you to memorize this part. Okay, got people ask me what is Ba? It is barium. It can be found in group 2 of your periodic table. Okay. Now, try and identify and circle all the soluble salts in your worksheet now. Can you go back and memorize the solubility of salts? I will test you on it next week. Okay, ungraded, but you should still study for it. Okay, can you try yourself before I review the answer? Pause the video now. Okay, so let us look at which salts are soluble. So first, is it a group 1 or ammonium ion? So I circle all the group 1 first, like your sodium chloride. Okay, any other group 1? Potassium oxide, hydroxide. Any other group 1? No more group 1. There's one ammonium salt though here. Okay, so I circle all the group 1 ammonium. Now let's look for nitrates. All nitrates are soluble. So nitrate soluble. Okay, now we need to look at it individually, case by case. Okay, remember that your chlorides are generally soluble except for silver and lead. So since this is not silver, not lead, this is also soluble. This is lead, so this is not soluble. Okay. Any other chlorides? Okay. So this is silver chloride is also insoluble. This is the example that we said. Okay. Now let's look at the sulfates. Sulfates are only barium sulfate, calcium sulfate, and lead sulfates are insoluble. So barium is insoluble, calcium is insoluble, but this is since it's not barium, not calcium, not lead, iron 2 sulfate will be soluble. Now, we are left with your oxides and carbonates. They are generally insoluble except for group 1 and ammonium. Okay, so since they are not group 1, not ammonium, these two are also insoluble. So this will be your final answer. 1, 2, 3, 4, 5, 6, 7 soluble salts here. Now we move on to types of oxide. Okay, students of 204 will start watching from this point. Okay, so recall what is an acid, what is a base, and how do acids react with bases. So acids, acids must dissolve in water to give H plus ions. What is a base? Metal, oxide, or hydroxide. How do acids react with bases? Okay, this will be a neutralization reaction. Okay, whereas your acid plus base gives me salt and water. Now you know what salt finally means, okay? Yay, good for you. Okay, now try and predict what will happen when dry ice is added to, first of all, water, second of all, aqueous ammonia in the presence of the universal indicator. Okay, try and predict what will happen. You must first know what is dry ice. Dry ice is actually solid carbon dioxide. Okay, and take note that it is universal indicator. So let's recall universal indicator. There's a spectrum of colors: red, orange, yellow, green, blue, indigo, and violet. Which is the neutral color? Green. This is the neutral color at pH equals to 7. Okay, so first of all, what color do you think the universal indicator will start with? What color will it end up becoming? Okay, let's watch the video. Video in a video section. Okay, so here is what you need: 2 cups, water, universal indicator of cabbage juice, ammonia, dry ice, and gloves. Okay, so note that it was initially green color, right? Okay, now let's continue watching. You see that the color has changed to orange. Yeah. Okay, so for the first reaction, your water plus CO2, your observation should be turns color from green to orange. Okay, let's continue on. This time is ammonia equals ammonia plus carbon dioxide. Okay, what do we have? Okay, now, why is this purple? Because ammonia is alkaline. Okay, so it should start from purple to, don't know what's the color yet. Okay, let's continue. Now you see, I add the dry ice. Oh, change to green, right? Change to green, yellow. Okay, we suddenly cut off the video. Okay, green. So we saw it until yellow lah, huh? Okay, so now let's try and explain what happened. Today we'll learn about types of oxides. So there are 4 types of oxides. Okay, generally, we can split it first into 2: the oxides of non-metal and the oxides of metal. When you are an oxide of a non-metal, you can be either categorized as an acidic oxide or, okay, acidic oxides, here are the examples, or it can be categorized as a neutral oxide. Here are the examples. So what does it mean by an oxide of non-metals? So you see sulfur is a non-metal, right? So this, since there's oxygen there, this is the oxide of sulfur. Okay, there are different kinds of oxides for a particular compound, as can be shown here. It can be SO3, it can be SO2. They are both acidic oxides. Okay, for your neutral oxides, there's only 3. So you must memorize these 3. Okay, if they give you an oxide that's of a non-metal and it's not these 3, it means it's an acidic oxide. Okay, can? Now, an oxide of metal can be categorized as either basic or, okay, basic or amphoteric. Okay, note. I asked you what's the definition of a base before, right? A base is a metal oxide or hydroxide. So that's why, of course, these oxides will be basic. Okay, and again, the amphoteric oxides, these are the only examples you need to know. So memorize. If you see another metal oxide and it's not these 3, it means that it's a basic oxide. Is that clear? Okay, so more stuff for you to memorize over the long weekend. Now, how do acidic oxides react? It reacts with alkalis to give us salt and water. So this is the definition. For example, just now your carbon dioxide reacted with your ammonia to neutralize it. Okay, to give us a salt, this is the salt and water. Most of them dissolves in water to give an acid. For example, just now, your dry ice example, you saw that it turned from to green to orange, right? Yes, orange. H2CO3. Okay, because this is acidic, you see there's H plus, right? So that's why your pH decrease. Okay, so this was green. Now it becomes acidic, so it becomes orange. Okay, so here is purple. Then when I add more acid, it will start to become neutralized, and this becomes green. When more of it dissolves, I get the acid, and it changes to become an acidic color. Okay? So there's one exception that does not dissolve in water. Silicon dioxide, it is insoluble in water, but it still can react with alkali. Okay, for example, this. Do you need to know what's the salt being formed? No need. Okay, don't need to know. You just need to know it is an example of an insoluble acidic oxide. But it is still an acidic oxide because it reacts with alkalis. Okay, I know this equation is quite hard to remember. It's hard to remember this, right? Okay, never mind. You don't really need to memorize this equation. You just need to know the properties. Okay, what is a neutral oxide? 顾名思义, it is neutral because it is neither acidic nor basic. Okay, it is also insoluble in water. An example is, okay, so what should be the expected observation when you do a litmus paper test on a neutral oxide? Okay, the moist blue litmus paper should remain blue, telling me that this is not acidic. The moist red litmus paper should remain red, telling me that it is not alkaline, not basic, sorry. Okay, so again, the three examples you need to know is H2O, CO, and NO. Okay, these are neither acidic nor basic. They will not react with acids or alkali. Okay, basic oxides are the ones that you already know. They react with acid to give salt and water. Typical reaction. They are mostly insoluble. Okay, do you remember what are the exceptions for metal oxides that's soluble? Okay, group 1, calcium and barium, dissolves in water to give hydroxide ions. They become alkalis, okay, when they are dissolved in water. Remember, alkalis are soluble bases that dissolves in water to give hydroxide ions. Okay, so note, they do not give O2 minus ions in water. They react with water to give you your hydroxide ions. Okay. Sorry about this. Erase away. So here's an example. Okay, your sodium oxide reacts with water to give you sodium hydroxide. What are amphoteric oxides then? Amphoteric oxides are kind of like both also want to be, okay? So they react with both acids and alkalis to give salt and water. Okay, for example, here's a reaction with zinc oxide with an acid, but zinc oxide also reacts with an alkali. Now, I know this one you can write, okay? This one you'll be like, huh? What is this, huh? Okay, you don't need to know how to write this. Don't need to know, okay? Just know that it reacts with both acids and alkali, and they always give salt and water. Okay, so in the presence of an acid, zinc oxide behaves like a basic oxide. In the presence of an alkali, zinc oxide behaves like an acidic oxide. So some see like that. Okay, yeah. So the three examples again that you need to know are aluminium, lead, and zinc oxide. Memorize this. Okay. What's important here is you need to know what type of oxide it is. When I give you an oxide, you must be able to categorize it and tell me, oh, this one only react with base, or that one only react with acid. This one react with both acid and alkali. you must know what type of oxide it is and what type of reaction it can undergo. Okay, so here's a video. Now, you are to predict what will happen when what will happen when zinc oxide is placed in a solution of HCl and in a solution of NaOH, both with universal indicator. Okay, so first, predict the initial color. Second, will there be a color change? Okay, change to what color? Okay, let's watch the video now. So one is HCl, one is NaOH. Now I'm adding zinc oxide to NaOH and zinc oxide to HCl. Okay, observe. Okay, now you see that the initial color for your NaOH was purple and it changed to green. Correct? Now, the initial color of your HCl was red, changed to yellow. Okay, you can see that if you draw the rainbow lah, red, orange, yellow, green, blue, indigo, violet. Okay, so from purple like violet, it shifts down. From red, it shifts up. Okay, so in different medium, zinc oxide behaves differently. Okay, so zinc oxide will neutralize both an acid as well as an alkali. Okay, bringing it closer to the neutral point. Okay, so you just need to memorize that these three will react with both acids and alkalis. Okay, now recap the whole thing again. Types of oxide. Think first, is it a non-metal oxide or a metal oxide? Non-metal oxide, it must be acidic. Okay, must be acidic except for these three. Okay, so don't need to know how to write the equation. You just need to know these are acidic, these are neutral. Okay, now if it's a metal oxide, generally basic. Some examples, except for the amphoteric ones, which only got 3 and you need to memorize. Overall, how many do you need to memorize? You only need to memorize 6. Okay, this one and this one, memorize. By default, they are all in this other acidic and basic category. Okay, so okay, I dropped the pace. Okay, anyway, that's another thing for us to go through in Sec 3. So that's all for today's video. Thank you for your attention. Please complete the quiz that I'll be sending you.